Okay, we've got a simple rational function here. Relatively simple just because the numerator and denominator each have degree 1. We want to find a horizontal asymptote, so we need to evaluate this limit to see if the function tends towards a constant or a finite value as we go to infinity. To do that, we divide through by the highest power term in the denominator. In this case, that's the x right here. X over x is 1. Now the idea is if you have a constant, a number, over x to any power, this goes to 0 as x approaches infinity. Now we should say here that this power is greater than 0. If it isn't, then things get strange. Alright. And so now we can just evaluate the limit as x goes to infinity of 4 over x is 0. 3 over x goes to 0. And we can evaluate the limit now to be -1 over 1 or -1. So y equals 1 is a horizontal asymptote. Vertical asymptotes. Vertical asymptotes occur where I have a number in the numerator divided by 0 in the denominator, a non-zero number up here in the numerator. Right, so of course the denominator here is 0 as x gets close to -3. So we want to look at the left and right limits as x gets close to -3. And we'll start from the left. So if we're a little to the left of -3, so x is in here, and we add 3 to that number, then we're going to be a little to the left of 0. So the denominator here is a small negative number. So we'll write this as 4 minus -3 over a very small negative number, 7 over a small negative. That tends to minus infinity. Similarly on the other side, if we start with a number a little to the right of -3 and we add 3 to it, x plus 3 will be a little to the right of 0. So here we've got 7 divided by 4 minus -3 is 7 divided by a small positive. So this limit goes to plus infinity. So we have a vertical asymptote, and we know from the left and the right the behavior. Where does it intersect the x-axis? So we need to solve f of x equals 0. Alright, a fraction is equal to 0 only when the numerator is equal to 0 and the denominator is not. So x equals 4 is the one and only x-intercept. Y-intercepts are easier to find. Where do we intersect the y-axis? Well, that occurs when x is equal to 0, so we just substitute 0 into the function for x. Okay, so that's at 4/3. Can we sketch the graph now? Well, we can get some idea of what the graph is going to look like. We know we have a horizontal asymptote at -1. Now functions can cross horizontal asymptotes. They don't have to, but they can. Right, we have a vertical asymptote at -3. You cannot cross a vertical asymptote. The function's undefined at -3. To the left of -3, we're going to approach minus infinity, so we're going down. To the right of minus 3, we're going to approach plus infinity, so we have to increase towards plus infinity. We know we have an x-intercept over here at 4. We cross the y-axis at 4/3. So perhaps the graph, if we're just trying to get a good idea what it looks something like this. As x tends to infinity, we're going to approach minus 1, and it's going to look somewhat similar down here. Now in this range to the left of minus 3, perhaps we want to actually plot a couple of points. So we could, for instance, plug in minus 4, minus 5, minus 6, just so we get sort of the right scale over here. All right. How do we compute this limit as x goes to infinity? Since we see a radical or a root here, that suggests maybe we can multiply by the conjugate. And by multiplying by the conjugate, we're going to turn this into a new problem, like one we've seen already. Sorry about the focus here. I'll turn that off so it doesn't bounce around anymore. There we go. Hopefully we see a familiar pattern here. A minus b times a plus b gives us a squared plus b squared. A squared minus b squared. Of course, we immediately see some cancellation. And now we're going to divide through by the highest power term in the denominator once again. In that case, we see an x here, and we see square root of x squared, so again x. So we're going to divide everything by x. The only difficulty is getting this x inside the square root. To do that, we're going to take x here and replace it by the square root of x squared. There's no difficulty with signs. X here is a positive number as we go to infinity, and squared x squared is positive. So that means under the radical here, we can divide through by x squared. X squared over x squared is 1, plus 4x over x squared is 4 over x, plus 1 over x squared. And now we're in a position to evaluate using the idea that as x goes to infinity, a bunch of these terms are going to 0. So the value of this limit is 2. Right. The squeeze theorem tells us, in this next problem, that if we have a function g which is stuck between two other functions, f and h, it's bounded below by f and bounded above by h, for all large x. So once we get sufficiently to large values of x, say past 1,000,000 or 2,000,000 or what, it doesn't matter, right? Then provided that happens, then as x goes to infinity, the limit of the lower function will be less than or equal to the limit of the middle function will be less than or equal to the limit of the top function. All right, what does that have to do with this? Well, sine x divided by x squared. Sine x is always between -1 and +1 for any values of x. But we're not interested in just sine x. We want to divide sine x by x squared, because as x squared gets large, we're dividing the numerator here, which is between plus and -1, by very large numbers. That should go to 0. Okay. So now we're going to take and divide our inequality by x squared. As we do so, now normally when we divide an inequality by a number, we have to pay attention that if it's a negative number, we have to reverse the inequalities. But here, we're talking about large x's, and x squared, of course, is going to be positive, so dividing through doesn't change anything. Of course, we need to make sure x is not 0 here, but that's not a concern because x is supposed to be large. Now as x goes to infinity, what the squeeze theorem tells us is once we have our sandwich inequality here, we can put limits on each term. Of course, this limit is 0. So our sandwich inequality, we can put limits on each term. And of course, this left limit is 0. That's less than or equal to the limit as x goes to infinity, what we want here. And that's less than or equal to this right-hand limit, which is 0. All right, the only number that's stuck between 0 and 0 is 0. So by the squeeze theorem, we know the limit as x approaches infinity has to be 0. Sorry, it's a little rough with moving the paper around here. I'm just getting used to sliding the paper around on this cam. This first problem on the next page, number 4 here, gave a number of you some trouble. All right, and that's because of the absolute values here. Let me review absolute value for you just a little bit. Okay. Remember, the absolute value of any number x is equal to just x if x is greater than or equal to 0. But if we put an x in here which is negative, I have to turn it into a positive, and the way we do that is by putting a minus in front of that x. So for x less than 0, the absolute value of x is given by minus x. What does that have to do with this problem? Right. Well, notice if x is a little to the right of 3, we have 9 minus x squared is going to be less than 0. Right. If x is a little bigger than 3, then x squared is going to be a little bigger than 9. 9 minus x squared will be negative. So the absolute value of 9 minus x squared, then, the thing inside the absolute value is negative, so I have to add a minus sign in order to turn it into a positive. And this is the same as x squared minus 9. So let's just repeat that here. Since x is a little bit bigger than 3, 9 minus x squared is a little bigger than 9. 9 minus x squared is negative, so I have to add a negative sign in order to make the quantity here positive. So this would be minus 9 minus x squared. And a lot of you are missing that minus sign right there. So factor in the numerator. We see that. Now we can factor and cancel, so we cancel out the problem, and now we can evaluate using direct substitution. So plugging in 3, we get minus 3 plus 3, negative 6. A removable discontinuity is a spot where the function isn't defined, but it has a left and a right limit. So that means our graph has a hole in it. For instance, that'll work. All right. If I plug in x equals 2, I of course get 0 over 0 here. However, the limit as x goes to 2 of f of x, I do my factor and cancel thing. It's already factored, so now I evaluate and I get 3, of course. So what does the graph of f look like? Well, essentially, at every location except x equals 2, I can just cancel off this term. And I'm talking about the line y equals x plus 1. And as I head towards x equals 2, the function wants to be at a height of 3, but it's not defined there. So this is a line with a hole in it. Alright, only thing to watch for here is whenever I solve a problem with logarithms, I have to make sure that the solutions I get at the end are valid. A logarithm can only take numbers which are greater than 0. So my first property of logs, the sum of logs is the same as the log of the product. Using the definition of logarithms, log base 2 of something equals 3 is the same thing as saying 2 cubed equals the inside here, or 8 is x squared minus 2x. It's a quadratic equation. The way we solve quadratic equations is to move everything to one side. Factor. Factor if you can. You could use the quadratic form if you can't factor. So x equals 4 or x equals minus 2. But if you're solving an equation with logarithms, check your answers. If I plug in x equals 4, I have no problem here. I can x equals 4 fits here, it fits here just fine. But x equals minus 2, I'm trying to take the log of a negative number, so we have to get rid of that solution. The only solution is x equals 4. To find the slope of the tangent line at a particular value, it's easiest to build that value into our limit. So the slope is equal to the derivative at a point. If I need the tangent line, the slope of the tangent line at more than one value of x, or more than one value if you want to call it a, then I might want to work out a formula. But at one particular value, I can just work the limit, focusing only on that spot. So here I need to plug 1 plus h into my function. I get 1 over my number squared minus 1 over my number squared divided by h. I see fractions, so that tells me the trick I need is to use a common denominator. I'm writing the divide by h here as 1 over h. What's my common denominator going to be? It's going to be 1 plus h squared, so I get 1 minus 1 plus h squared. You might need to take a second off to the side and make sure that you buy this, that you agree. Watch this minus sign. So now we're going to expand the numerator. One minus 1 is 0, minus 2h minus h squared. And I see that I can cancel out the bad h. I've got a common h here, which I'll factor out. Now that I've canceled the bad h, I can use direct substitution to allow h to go to 0. Alright, one last problem here to complete this quiz. Alright, this is a kind of a pre-calc problem. We have a model here for population growth. And we know that our model has this form. It's exponential. And we need to identify the growth rate, r. Okay. And to do that, we have a piece of data here. We know after 3 months, so when t equals 3, we know that the population y is equal to 5,000. So we're going to plug that data into our equation. To solve a problem involving an exponential, it's easiest if you isolate the exponential first. So I divide 5,000 by 2,000, cancel some zeros, and I got 5 halves equals e to the 3r. Now I can apply the natural log to both sides. 5 halves is the same as 2.5. I take the natural log of e to the 3r. Natural log and e are inverse functions, so they cancel each other. And I get r is the natural log over 3. Now if you pick up a calculator and evaluate that as a decimal, you should see forgive me for a second here, I'm shopping around in my notes. The 4 decimal places, 0.3054. At what time is the population going to be 20,000? I plug in y equals 20,000 into my model. I know the value of r, but I'm just going to write it as r for now. And now I need to solve for t. Dividing both sides by 2,000, I get 10 e to the rt. Natural log both sides. Solve for t. And I can put in the exact value from above, or I can use the decimal approximation to r. And since I just need to know the value of t to 1 decimal place, that should be sufficient. So after about 7.5 months, the population will be at 20,000.